let's talk through very quickly several of the issues around exponential growth and decay. First, exponential growth is in fact a very ordinary thing. You see it in savings accounts, you see it unfortunately in credit card balances, you see it in mortgages, but there are some other things going on in mortgages because you're paying it off on a regular basis. One of the reasons we worry about global warming is it's an exponential growth process. So anytime there's an exponential, you really worry about where are you on that and how long do you have to actually do anything, which we'll see in some of the problems in this section. There are variable rates in exponential growth and decay. So the simple one is b of x here is simply a constant. So whenever b, the rate of change of the quantity of whatever you have. It could be kilograms, it could be concentration, it could be moles with respect to some other variable. X times 1 over the amount you have at a time is a constant. That's when things are constant, you get a simple exponential. Here we have a variable rate b of x. So over time that rate changes. And in a lot of our problems, this x, don't think of it in these equations as what we typically use it for in regular physics, which it's a position, it's just a variable. So very often we're more concerned about time. So let's rewrite this as b as a function of time is 1 over the amount of something you have times the derivative of what you have. And this can be solved. And what you get is your concentration or your amount, or let's go with concentration in a minute. At the moment, your concentration at time t2 divided by your concentration at time t1 is e to the, that's what this exponent function is, the integral of b of t dot dt over that time period. An integral is just adding up b of t times dt in very tiny slices from time t1 to t2, and you'll see this again in the problems and example where I do a little bit of this in Excel, and then we do the integral. So this gives us y of, and if you t2 over y of t1, right? It gives us proportions. And to what extent have things changed? Another concept you're going to run up against clearance and chemostat. The concentration of material is just the amount you have per unit volume. So concentration is Y over V. Y is the amount of material, V is the volume of the fluid the material is in, right? So you've got material dissolved in something. So let's say you've got 5 milligrams of sodium chloride in a liter of water, right? The concentration is 5 milligrams per liter. The clearance, K, is in cubic meters per second. And in biological systems, we often talk about the clearance of something because let's say I have an excess of some material in my body. The number of liters per second of fluid in my body that are being cleared of the material is the clearance. And so that looks like as an equation, the change in concentration per time is minus the clearance times the current concentration, right? And so this minus K Y over V, the change in the amount I have is minus K times concentration. And you can solve this pretty simply. It's a nice, easy exponential equation. So you've got an initial amount you have. Let's say I just had dinner and I ingested for some ungodly reason 100 milligrams of salt. Well, this describes the exponential decay as my body deals with all of that and slowly clears it out of my system, right? So e to the minus the clearance over the volume that we're dealing with. So if we're talking about my blood volume, 5 liters, 6 liters or so over time, times time. The chemostat equation is related but not the same. And here's what the chemostat equation says. You got a growth medium for bacteria, let's say, and if you just let it sit there and the bacteria will eventually consume all the resources. You've got to keep feeding them, basically. Well, that means you have to replace some of the nutrient, and you're doing that at some rate Q. And in that nutrient that you're pulling out to make room for the new nutrient, there are some bacteria. And so you've got the rate of change in the number of bacteria is their growth rate, B, times the number of bacteria, minus Q, the nutrient replacement rate, times the concentration of bacteria, because that tells you how many bacteria are going out with the trash, right? And so you've got the growth of the bacteria minus what you're throwing out with the trash. You end up again with an exponential function in the chemostat equation. Decays happen all along all kinds of different ways, but when you look at a radioactive material in on the periodic table, um, those elements typically have more than one decay path. And the one that we quote as the decay rate is actually the sum of all the different paths. So the amount of material you're losing per second is minus the decay rate for each path times the constant amount you have. In terms of half-life, T, it is that 1 over T1, the half-life for one process, plus 1 over T2, the half-life for another, plus 1 over T3, plus etc. All that adds up to 1 over the half-life. And if you'll remember from pipes and resistors and everything else, you'll recognize there's a pattern. The parallel processes end up adding inversely. Decay plus input at a constant rate is very similar, but now you've got your decay rate, but you've got new material coming in at some constant rate. And that gives you your amount of material at any time is A over B onto 1 minus e to the minus b over t. The logistics equation accounts for the fact that exponential growth has its natural limits. Let's take the current pandemic. There are only roughly 8 billion people in the world. Once 8 billion people have been infected, no more can be infected. So it's not an exponential out ad infinitum. And the way we look at the logistics equation is this. Down near the low end, when y is small, the growth rate looks like your growth rate times y, or your growth rate b naught onto y. So dy dt just b naught y. Well, as y becomes large or approaches whatever its limit is, whatever the limit of y is, well, this y over y naught becomes 1. You get 1 minus 1, and this whole thing tends to 0. The change tends to 0. Right? The solution to this logistics equation is here. Y of t equals y naught, y infinity, over y naught plus y infinity minus y naught, e to the minus b naught t. Right? So y naught is y at t equals 0, y infinity is y at t equals infinity, and b naught is the initial growth rate. All pretty straightforward, even though it looks scary on the page. Finally, and this is a great little study and production of Kleiber's law. So unicellular organisms, really simple organisms, the rate at which they consume energy, right? And this is watts. The rate at which they consume energy is 0.018 times 10 to the 0.751. That's this group that fit this line down here. The next group up, poikilotherms, things like fish and jellyfish, things that don't have their own independent temperature but are at the temperature of the environment. They have a slightly different behavior. The only change is out front, right? This m is their mass, 0.14 times m to 0.751. And so you can see your mass to the 0.751 times a different factor. And then homeotherms, like us, we have a temperature that is largely independent of our environment until we're in extremes, right? There, the multiplier is 4. 4.1 times m to the 0.751. So if you wanted a basic estimate of metabolic rate for any particular human, let's take a large one like myself, 4.1 times 75 kilos, no, 85 kilos, let's say, to the 0.751, and my basal metabolic rate, the rate at which I consume energy just sitting around, is 115 watts. All right, and that kind of dictates a lot of things about diet and stuff like that. Basal metabolic rate contributes to different aspects of diet. So that's the quick overview of this chapter. Good luck with the reading, and I'll talk to you soon.